Hey everyone, ever stop to think about what actually keeps your bank details safe when you shop online? Or what makes your private messages, well, private? It all comes down to this incredible process that acts as the guardian of our entire digital world. Today, we're going to pull back the curtain on encryption.
So, think about this for a second. You're sending an email, buying something from a website, or saving a really important file. What is the invisible force field that's standing between that information and somebody who shouldn't be seeing it?
Well, you guessed it, the secret is encryption. It basically creates a digital lockbox for your data. And to really get a handle on this, we're going to stick with a super simple but really powerful idea: a lock and a key.
Now, when you hear encryption, you probably think about stuff flying across the internet, right? But the story actually starts way closer to home. We're talking about the data that's just sitting there, on your devices. This is what the pros call data at rest.
So what is data at rest, exactly? It's really any information that's physically stored on a device. You know, your laptop's hard drive, the files on your phone, or even those gigantic corporate databases. If it's not actively moving across a network, it's data at rest.
So, when we want to lock this stuff down, we've basically got two main ways to do it. The first one is full disk encryption. This is like putting a massive padlock on your entire filing cabinet. Everything inside locked down tight. Your computer probably already has this with tools like BitLocker or FileVault. The other way to go is file-level encryption. This is more like putting locks on individual drawers inside that cabinet, giving you the flexibility to protect just specific files while leaving others easy to get to.
Okay, that makes sense for your personal computer, right? But what happens when you're talking about huge, massive databases, like with millions of customer records? Can you really just slap one big lock on the whole thing?
Well, yeah, you can. It's a thing called transparent encryption, and it does exactly what it sounds like. It takes a perfectly normal, readable database and just scrambles the whole thing into what looks like total gibberish. Without the key, it's just digital noise. That's some serious security. But there's a big catch. Imagine you need to find just one little piece of information, like an employee's ID. To do that, you have to unlock and decrypt the entire database, just for that one simple search. It's incredibly secure, but talk about inefficient.
So this is where you got to be smart about it. A much better approach is something called column-level encryption. You leave the easy-to-search stuff like names and IDs unencrypted so you can search them quickly, but you lock down only the really sensitive columns like social security numbers. It's the best of both worlds. You get speed and security.
All right, so that's data that's just sitting around. But what about when it's flying across the internet? I mean, most of our data is constantly on the move, and that's where securing data in transit is absolutely crucial.
And you see this all the time, probably without even thinking about it. You know that little lock icon in your browser's address bar? Yep, that's HTTPS at work, encrypting the connection between you and the website. Ever use a VPN? You're basically creating a secret, encrypted tunnel for all your internet traffic to travel through. So even if someone intercepts your data, it's completely unreadable.
Okay, so we know where we use encryption, but how does the magic actually happen? It really all comes down to two fundamental pieces: the recipe and the key.
So first up, you've got the algorithm. Just think of this as the recipe, the step-by-step mathematical formula for scrambling and unscrambling the data. And here's the important part: both the sender and the receiver have to be using the exact same recipe for it to work.
But get this, and it's going to sound a little weird at first. These super secure recipes, they're actually totally public. You can go look them up right now. And that's not a bug, it's a feature. It means that experts from all over the world have picked them apart and tested them, so we know they're solid.
It's kind of like the blueprint for a super secure door lock. Anyone can look at the blueprint and see how the lock is designed, and everyone can agree that, yep, that's a really good lock.
But knowing how the lock is built doesn't help you open it, does it? You still need the one secret ingredient, the key. And in the world of encryption, that digital key is what makes the whole system secure.
Which, of course, brings us to the next big question. If the whole system hinges on this one little secret key, how in the world do we make sure that key is basically unbreakable?
I mean, what's to stop a determined hacker from just sitting there and trying every single possible key until one of them finally works?
That's a totally fair question, and there's a name for that kind of attack. It's called a brute force attack. It's pretty much what it sounds like, just trying every single combination possible until you break in.
So how do we stop that? Simple. We make the keys ridiculously, mind-bogglingly long. A short key? Yeah, a computer could probably guess that pretty easily. But with modern 128-bit encryption, we're talking about more possible combinations than there are atoms in the sun. Seriously. The fastest supercomputer on Earth would need millions of years to even make a tiny dent. It's just not going to happen.
But wait, there's more. We have another really clever trick up our sleeve to make life even harder for an attacker. It's a technique called key stretching.
Okay, this part is pretty cool. Instead of just using your password as is, the system takes it and runs it through this complex mathematical process, a hash to encrypt it. Then it takes that result and hashes it again, and again, and again, thousands and thousands of times. What this does is it forces a hacker's computer to do a ton of extra work just to test one single password. It slows them down to an absolute crawl, making a brute force attack totally impractical.
So where does all this leave us? Well, it's pretty clear we're in this constant cat and mouse game, right? As our technology gets more powerful, the tools for the bad guys get more powerful too. We're always building stronger locks, and they're always finding smarter ways to try and pick them. The principles of encryption we've covered today are the very bedrock of our digital security. But this is a race that, honestly, is probably never going to end.